I am Kamil Yenice. I work at the University of Chicago. I've been here for 14 years. Prior to this, I was at Memorial Sloan Kettering Cancer Center in New York for a number of years, also doing radiosurgery there. Since I don't have a camera that you can see me, I put a picture of me. When I'm not in the office, I hang around in places, exotic places. This is what I look like. And those of you who cannot see me because I don't have a camera, this is what I look like. And this is what our campus look like, an aerial view on a nice day. University of Chicago, it's on the, in Chicago by the lakefront. It's an old university, private university. And this is our medical care campus. From the campus, you can see the city. We are on the east side of the city. Not always it is sunny in Chicago. We recently lived through a polar vortex of 2019, and it looked like this with temperatures in -20 Celsius and more. But now, today, it's not that cold, so we are lucky. It's a little bit rainy, but it is otherwise nice. So today, I will talk about radiosurgery. And some of you, or maybe most of you, have been practicing radiosurgery, and you know what it is. But briefly, radiosurgery refers to the use of radiation as a surgical tool, which means small volumes of tissue within the brain are treated with large doses delivered in a single fraction. Because of single fraction delivery, the radiation acts like an ablative agent, like a knife. That requires very precise delivery. And in order to protect the normal tissue surrounding the lesion, any lesion that is treated, rapid dose follow-up needs to be established. This is done by delivering the treatment with very high precision. In radiosurgery, because it is ablative and it is invasive, in a way that radiation, delivers this very radical treatment. And the most important elements are whether you know where to aim, in other words, target anatomy localization. It's a common problem for all SRS modalities, regardless of what modality you use. And the second issue is whether you can hit what you are aiming at. That refers to dose localization. It is procedure, process, equipment, technique specific. Now, to address do you know where to aim? In the beginning, from the beginning, there are tools developed to determine the exact coordinates of the tumor. For this purpose, stereotactic frames have been developed. Stereotactic frames provide three functions. These functions are to immobilize the patient. It provides a rigid fixation of cranial anatomy. It provides localization, target localization, which is the precise identification of target coordinates in a stereotactic coordinate frame. It provides also treatment setup by means of patient setup with the placement of target coordinates to the nominal isocenter of the linac. In this figure, we see a frame attached to patient. That's the halo. And then there is a localization frame that is attached, and the patient is CT sim, where the patient anatomy is delineated, and also the localization rods are indicated in the CT, axial CT images. The localization refers to precise finding of those rod coordinates, and then building a coordinate system, and everything else is referred to those that in that coordinate system from that point on. Now, determining The target whether you know where to aim, it requires to determine the exact shape and size of the target. But this is not a simple task, actually. It requires that physicians look at those images we acquire in the clinic, and then they identify the targets in these images. This is a study done in Japan by 11 clinicians in 7 CyberKnife centers. They evaluated 21 plants, and they were looking at different type of targets, pituitary adenoma and meningioma. Those highlighted contours show the delineations or contours entered by different physicians. And you can see the volume of the targets significantly changed based on which physician entered those targets. So there is a large uncertainty in the determination of the exact shape and the size of the target, depending on the indications. In this case, these are pituitary adenoma and meningioma. There is another study. This is done by using CT versus CT plus MR. And in this study, Weltons et al. Published in 2001 showed that by using CT together with MR, you can actually improve that the accuracy of target delineation. So, in other words, we need more tools to improve the target definition, which is very important element in radiosurgery. For this purpose, most modern thermal planning system that is used for radiosurgery use CT and MR registration or fusion, so that you can delineate the targets on both CT and MR to remove any ambiguities. CT provides high spatial fidelity because it is geometrically more accurate information, and MR provides better or enhanced soft tissue contrast, but it has nevertheless reduced spatial fidelity. By combining the two, we get more accurate target definition. In some cases, like AVMs, we also utilize other imaging modalities like angiography or digital subsection angiography images, and they are typically registered to CT images to delineate the AVM nidus. In this case, angiography helps identification of the nidus position and differentiation from feeding arteries and draining veins, which are not easily identifiable on CT and MR images. But the extent of the nidus can be defined on CT angiography, and typically this is done in a CT fashion. Once you determine your target precisely, the next issue becomes whether you can hit what you are aiming at. And this refers to dose localization, as we mentioned before. Now, the radiosurgery is delivered historically, first by gamma knife, and then implementation of radiosurgery techniques on linear accelerators by means of in-house developed hardware, but more recently, in the last 10 years or more dedicated linear accelerators by various vendors. In early 2000s, Brainlab developed, along with Varian, a device called Novalis TX. This was the first device using fine MLC leaves with 2.5 millimeter leaves, and this was called the Novalis machine. It was more later developed, actually, or more advanced. In the current version on the Varian platform, now TrueBeam STX uses the same kind of technology with HT-MLC with fine leaf MLC leaves, with even flattening filter-free beams using 6 MV or 10 MV beams at the dose rates of 1200 MU or 2400 MU per minute. This machine is also equipped with onboard imaging and in-room KV imaging from BrainLab, which provides also robotic 6D positioning. This helps delivery or dose localization process in the next stage. Varian is not the only vendor. Elekta also provides Linac-based radiosurgery solutions. They have more recently a micro MLC attachable to the device, and they also develop a new MLC with finer MLC leaves with 4 millimeter leaves. They also provide various tools, and during the acceptance testing, actually we do this in most centers. When you accept a machine, they bring those tools, they attach this pointer, and they attach this cone system on the head of the machine, where you target this, and then you can measure the isocentricity of the machine. In our center, we did this test, and these are the images that are taken with the panel, MV panel, at various various gantry angles, and also couch kicks. At the acceptance testing or at the installation, in our machine, these are the results that we received from these measurements. The gantry collimator isocenter offset was found to be less than 0.5 millimeter, and that is the acceptance test criterion of Varian. In our center, this was measured to be 0.3 millimeters. Combining all three axes coincidence, gantry, collimator, couch offset was required to be less than 0.75 of a millimeter, and in our center we measured this to be 0.6 millimeters. So this indicates the radius of a sphere in which the axis of all those different elements of the machine can rotate within this precision. In other words, the machine can deliver the radiation within this accuracy. But this is not the only accuracy that actually, or the element that goes into the total accuracy. Most of the time we use onboard imaging, KV imaging or cone-beam CT imaging, and we also do MV KV coincidence test. For this purpose, Varian also provides a tool, and I think Elekta also has similar tools. With this, they determine the KV and MV isocentric coincidence to be less than 0.5 millimeter. Typical result is about 0.2 millimeters for our machines. Now compare this to Achievable Uncertainties in Radiosurgery, as published in 1995 with AAPM Task Group Report, TG42. At that time, technology was not this sophisticated. They relied on stereotactic frame, and machines can provide isocentric alignment within 1 millimeter using 1 millimeter CT slice thickness, and accuracy or uncertainty of 2.4 millimeter can be achieved. If you were to use 3 millimeter CT slice thickness for planning, using these numbers in quadrature, you could get 3.7 millimeter deviation. These are the Achievable Uncertainties published in 1995 with frame-based alignment or frame-based positioning. Prior to now, IGRT, if you use IGRT still cannot remove existing registration uncertainties, so this still remains. And we earlier said MRCT registration is important for target delineation this also has some uncertainty in the order of 1 millimeter. So keep this in mind. In the planning process, this will become an issue, and then we will try to come up with a margin. Most of the time, radiosurgery, the neurosurgeons, are not used to using any margins, and in many centers, radiation oncologists follow the same suite, and they don't use margins. But if you were to use a margin or determine the uncertainty in the process, you can use a margin recipe typically published by other investigators. This is a typical margin that is used in radiotherapy, which is equal to 2.5 times systematic error standard deviation times 0.7 times random error standard deviations, published by Van Hert et al. In 2000, using analytical solution to analysis to a scheme to cover the CTV, in this case the GTV, for 90% of the patients with the 95% isodose line. That requires a PTV margin of 2.5 times the standard deviation of systematic errors plus 0.7 times the standard deviation of random errors. This is actually, there is a larger number here in front of the systematic errors because systematic errors have more impact on the treatment. That is why this number is larger than this number. Now, in the era of IGRT, when you combine it with stereotactic radiosurgery, how does this play? Now, for a typical case, if you don't use invasive frame and if you use mask system for immobilization, you still have other sources of error in the process, like delineation, organ motion, setup error, cone-beam CT, accuracy, that has to be included in this consideration. Now, delineation is a systematic error. That's why it comes in this column. So I have two columns here. One is systematic errors that indicates actually this large sigma, and second is the random errors, which indicates this small sigma. Okay. In this column, I have delineation. This is what the physician actually enters. Typically, if you use a good MR and CT for metastatic tumors, which are very well delineated or well exhibited on those images, you get a delineation error of 0.5 millimeters, which is typically the pixel size. Pixel size for a CT image is in the order of 0.5 to 0.8 millimeters. NMR is not any better. And organ motion, schematically, there is no organ motion, so it is 0. And the setup error is in the order of 0.3 millimeters. And there is no interfraction motion schematically you can actually take. So the total error in quadrature, you add up to 0.6 millimeters. For random errors, we have only in this bin interfraction motion, which is in the order of 0.2 millimeters. So that comes in here. When you add everything actually here, the total margin schematic errors are 1.5, and random errors in the in the order of 0.14. When you add them up, they are in the order of 1.7, just under 2 millimeters. So that is the tightest margin achievable in external beam radiotherapy or radiosurgery using IGRT due to a well-defined MR outline. Now, most of the time in the clinic, people don't use it because, first of all, the largest error here that contributes to this big number is this one, which is because nobody actually really cares, or does. I don't mean to, care, but they don't actually consider this error. But if you were to put an uncertainty budget here, actually, on these different factors, this will come into play. So when you talk to your physician, you can, enlighten the physician in terms of these type of sources of error. So in conclusions, interfraction movement in a mask is about, if you are using mask, is about 0.2 to 0.3 millimeters, which is comparable to registration accuracy of images. With automatic couch shift, the accuracy of IGRT is extremely high, especially with robotic couches. Rotational errors have negligible effect for CTV or GTV coverage in most cases. This is typical for classical isocentric targeting. In other words, the target or the tumor is targeted so that the isocenter is placed in the center of the target, not necessarily for cases for single ISO multiple MET. This is a different type of indication. It requires consideration of those rotational errors explicitly. Combing CT guidance of stereotactic treatments achieves comparable results to methods based on invasive frames. So you can actually do just as accurate, if not more accurate, with frame-based systems. So I'm gonna change the gears. If you are doing linear radiosurgery, what type of beam shaping are available? Typically, for shaping the beams, we use tertiary collimating systems using circular cone inserts anywhere from 5 millimeters to 40 millimeters in diameter. These are precisely machined inserts, and they are placed close to the patient, and they provide smaller geometric penumbra with diverging beam shaping further minimizes the penumbra. You can also have MLC beam conformal beam shaping. They can the field shape conforms to the outline of the target. This way, you can provide more uniform intensity across the field. Non-target tissue radiation is minimized by conformal shaping, and this is typically done in most modern radiosurgery techniques. Now, when you have this type of beam shaping available, what can you do? What type of treatment options you have? You have circular arcs where you use this circular, fixed circular beam size, beam shaping, or conformal beam with MLCs, or dynamic conformal arcs. When you use these, you use circular arcs for small symmetrical targets. In other words, like trigeminal neuralgia or small metastases. When you use the conformal beams, you use it to specifically avoid normal structures and for targets too large for dynamic conformal arc. And you use dynamic conformal arc, use it for most cases except larger lesions. You can also do IMRT capability for irregular targets or fractionated radiosurgery. Now, the treatment process is typically involves, if we are using frame-based, first it starts with the frame placement, which provides rigid immobilization, or you can do frames approach where you can simulate patient or you can immobilize the patient in a mask, and then you can simulate the patient with that immobilization technique. And then it requires treatment planning. Obviously, if you are doing rigid immobilization with a frame placement, the treatment planning has to take place on the same day. Then you do evaluate the plan, you do QA, and you do treatment machine and patient QA, and you set up the patient and treat the patient. The basic rules, of treatment planning: the placement of the isocenter. Typically, it is placed at the geometrical center of the PTV if you have a single target, and the cone size for a circular cone is chosen to encompass most of the target volume. Choice of the arcs or beams based on the knowledge of the 3D anatomical information, size and location. Nowadays, the treatment planning systems provide you visual tools to place these beams in a very informative fashion where you can avoid any unnecessary sensitive structures in the beam, And you can also minimize the radiological depth to the lesion to further minimize the dose to normal tissue. Normally, you are supposed to separate the arc planes so that those beams don't overlap. That also depends on the collimator size. These are the basic rules for manual plan optimization: selection of the arc length and position, beam number and position. So you can limit number of beams arcs in anterior posterior direction so that they don't overlap. The rules, you need to get at least anywhere from 8 to 9, maybe more, non-coplanar beams which are not overlapping. And typically you can space arcs up to 4 to 7 or beams 11 to 15. For ellipsoidal lesions, you can differentially change the arc weighting so that you can pull the dose in one direction, maybe to fit the ellipsoidal lesion shape. You can use multiple isocenters if the lesion is irregular or large, and you do a kind of gamma knife type of planning with multiple sphere packing type of plans. For irregular shapes, use of multiple isocenters for circular cones, as I said, or either high definition MLCs for conformal beam shaping, for using static beams, arcs, or dynamic conformal arc techniques. There are publications in the literature. These actually provide very nice guidelines. This is the published University of Florida paper from early 2000s or maybe late 1990s, showing their 5-arc technique. They have this standard beam or arc angles. If you notice here that they don't have zero table angle because they avoid overlapping beam at zero table, but you can actually use zero tables. It will be just fine as long as you don't actually oppose those beams. In this case, their standard approach was 20 degrees couch angle here and 340 degrees on the opposing side, and then 270 degrees or 90 degrees, and then 55 degrees on each side at these different positions of the couch, getting different approaches to the lesion. Depending on the location of the tumor, they will eliminate some of these arcs, or they will actually increase the arc span. This is a multiple isocenter planning using circular cones. This is kind of nowadays became almost archaic because most linear accelerators are now equipped with MLCs. This is actually at the time when the linear accelerators didn't have those fine MLCs, but you could actually achieve this very conformal beam plans. However, it is highly inefficient treatment delivery process with the LINAC. Nowadays mostly replaced with MLC-based treatment planning and delivery. You can do this in a more elegant fashion using conformal beam type of treatments. The first application of this was in mid-1990s to late 1990s by use of this micro MLC from Brain Lab. Nowadays, this was also further advanced by integration of those high definition MLCs within the linear accelerator system. You can maximize the solid angle as shown here. You can approach from many different angles, but however, you need to use a reasonable number of beams. And how many beams are reasonable? Typically, after 11 beams, you don't actually get more gain. Actually, the higher the number of fields, the lower the peripheral dose, but there is also a limit to that, and that turns out to be about 11 beams. But the main thing is use unopposed fields so that those fall off outside the target is optimized. This paper gives a good overview of how many beams you need to use, and they say typically 11 static conformal beams, non-opposing beams will be sufficient to get very sharp dose gradients. Now, in a LINAC radiosurgery, in general radiosurgery, the question comes, what should be the prescription isodose line that is covering the target to get the best dose fall-off? Now, in the radiation therapy, we typically use 90%, sometimes 95% or higher. But for radiosurgery, it turns out this is actually the typical dose fall-off curve. This is multiple isocenter and multiple beam planning. What I did, I took actually calculate dose profile across this dotted line, and then I show the dose fall-off across. I mean, actually, from this shoulder of the beam profile covering the target. Now, this shows that if you were to normalize the target to 90% isodose line and then look at the dose fall-off to half of its value at 45%, that the penumbra actually will be like almost 6 millimeters. However, if you do that actually for, if you normalize the dose to 80%, in other words, at the tumor margin, the dose that is covering the prescription isodose line that is covering the tumor will be 80%, and then look at the 50% of the dose fall-off, you will calculate that that distance will be about 4 millimeters. It turns out normalizing the dose to 80% for most LINAC isocenter LINAC techniques provides the best or more optimized dose fall-off. That is why for most single isocenter plans, typically dose is prescribed to 80%, and multi-isocenter cases, people's dose fall-off region moves near 70%. In comparison, Gamma Knife is typically requires a 50% isodose line prescription to provide the steepest dose fall-off. These are some plan examples. This is very actually unusual type of case. I put this one to show that actually even this type of a plan can be delivered using linear accelerators, using MLCs. So this is, I look at this slide from literature. This is actually one of the talks given by one of the speakers in one of those conferences. They talk about small field targets, how to shape, and it talks about SBRT or SRS in CNS cases. Typically, beam shaping is done by cones for cases like trigeminal neuralgia or functional treatments requiring cones of 4 millimeters or in that order, or the largest beam mets 40 millimeters in diameter. We look at this. I'm not going to go into detail, but we've been. Is there a question? Okay, we've been using MLC-based treatments for years, even for very small targets such as trigeminal neuralgia. And we recently published a paper to show the validation of MLC-based near accelerator radiosurgery for trigeminal neuralgia. This shows a typical plan with beams in the order of 20 plus, with multiple between the nerve and the brainstem. So we did actually three things: verify the MLC shapes for these very small targets, verify the isocenter placement or the dose localization, and then verify the delivered total dose for these very small targets. And then we did several things. To verify the shapes, we did, first of all, we took 9 cases which were prescribing 60 to 90 gray isocenter in a single fraction, and PTVs range from 0.03 cc to 0.07 cc with a mean volume of 0.04 cc. And we look at these plans, and they typically use anywhere from 18 to 21 beams. with an equivalent square field size of 0.6 millimeters or 0.6 centimeter to 0.7 centimeters. In our case, we restrict the minimum field size to smallest field size measured beam data, which is the 0.5 cm. We are using HDMLC on a variant machine with a 0.25 centimeter leaf width. A plan use these kind of beam apertures with this kind of beam dose fall-off. And we look at what we did. We delivered this in a portal imager device, and then we look at the position of those leaves from the analysis of those images. Altogether, we had more than 1,200 samples with approximately 20 fields per patient. Each one of those beam apertures typically had 8 MLC leaves involved to define each leaf, each field. We also did dosimetric analysis. We did a phantom. We inserted a very small dosimeter using a scintillator detector with a size of 1 millimeter to simulate a trigeminal nerve. And then we measured the dose delivered to this target under image guidance, just like we would treat a real patient. And then these are the results between the calculated doses and the measured doses. And these are the differences between the delivered doses and the calculated doses. So from our analysis, we did actually deliver the correct dose to those patients or the representative cases in a phantom within an accuracy within 3% overall accuracy. And in the final stage, as I said, we wanted to determine the end-to-end dose localization or isocentric verification. To do this, we did a planar film testing in the same phantom with the inserts, and then determined the location of the isocenter on those films, and then did the gamma analysis using global gamma. And this slide summarizes the width, full width at half maximum of these measured profiles versus calculated profiles, and the difference between the measured and the calculated profiles. So overall, we are confident that we can deliver those treatments with the HDMLC with 2.5 millimeter leaf width. That is the take-home message from this study. For patient treatments, you need to do SRS treatment, specific treatment, QA. Typically, you are supposed to do this known target test, stereotactic localization, just like what I described here. You need to do also test whether, even with the frame-based system, you need to verify that the patient is immobilized rigidly. If you are using the mass system, you also need to document or confirm that the patient doesn't move during the treatment. And then you need to also rigorously verify the treatment setup. What we do, we also daily output verification of SRS beams, typically the flattening filter free beam or the SRS mode for another type of machine. You are also supposed to do daily IGRT QA, MV and KV imaging coincidences if IGRT is used for setup, IMRT QA if IMRT used in the treatment delivery. This is kind of an old technique, but if you are using a frame-based patient setup and localization, you have to do redundancy checks for the SRS coordinates with the phantom pointer. And this only comes with one vendor in the US, and they don't actually, they are not even actually available anymore. But whatever system that you are using, that you have to confirm the stereotactic radiosurgery coordinates independently, and then you need to do a redundancy check with respect to room lasers. And then at the final stage, you need to validate the treatment position using either COMBEAM CT or OBI imaging. We did this study also using the OBI imaging and cone beam CT, and cone beam CT setup accuracy is in the order of a millimeter with a standard deviation of 0.3 millimeters from phantom studies. Now, there are cases you cannot do in a single fraction, and then what are you supposed to do? Then you can do actually fractionated stereotactic radiotherapy or SRT. Those are typically reserved or done for larger tumors, larger than 4 cm, or tumors involved with a critical structure. Sometimes there is an indication with a tumor close to a sensitive structure or radiosensitive structure, and it cannot be treated with a to a high dose, because the dose follow the distance between the tumor and the structure is not large enough to allow enough dose follow. In that case, you can provide guidance to physicians that this, and also they might ask you to do this too. You can do the treatment in a fractionated fashion so that we can take advantage of biological tissue tolerance of those two different types of tumors. You can do this conventionally or hyperfractionated fashion, then take advantage of the radiological difference between the tumor and normal tissue response. There are two different types of mask systems that are used for the fractionated treatments. This is an old mask system using mouthpiece immobilization with an occipital support. This is from Brain Lab, and there are other types of masks. They all serve the same purpose, but you need to make sure that the masks immobilize the patient to a sufficient degree of rigidity so that you can actually correctly do this. Most face mask systems, they don't actually, you have to check their immobilization accuracy in the order of a millimeter or so. And if you are not actually using IGRT, achievable localization accuracy with these systems are not better than 2 to 3 millimeters. So they require some sort of IGRT approach regardless. Image guidance improves the setup accuracy with these systems. In recent years, there is optical imaging systems available in treatment rooms, and they are combined with cone beam guided systems. And one of the implementations is used here. This utilizes both a mask system and also a mouthpiece localization, immobilization, along with a visual system, which casts a pattern of spec images, spec pattern on the patient, and those camera systems can recognize those patterns on the patient, and they determine the patient position from those three parts. And then you combine this with the cone beam image to determine the patient position. There are multiple publications in literature. One of the early ones that is actually published in Medical Physics in 2011, and there are more recent ones. There's also an AAPM-TG task group effort recently working on this work, combining the use of visual optical imaging for patient treatment setup, not only for radiosurgery, for other type of treatments. These people also demonstrated that using very accurate or very precise surface imaging, you can determine motion monitoring. Even with this semi-rigid patient setup, they determined that patient motion can be still can still exist there in the order of a millimeter. Sometimes patients position changes even in a mask system in the order of a half a millimeter to a millimeter. That is why you need to have a robust system to determine whether the patient is in the same position. And when you position the patient for final treatment position, you need to do final verification with the IGRT system that you have. Finally, fractionation offers favorable outcome also. So this is a study comparing the single fraction versus fractionated treatments, the local control, local progression-free survival rates, and the in both groups were at 6 months and 1 year were 81% and 71% versus for the SRS group versus 97% and 69% respectively for the FSRT group. So FSRT is another alternative, and it is very favorable in most studies. It can be used for accurate treatment delivery. So in summary, current linear accelerated technology presents significant capabilities for radiosurgery applications, including improved mechanical accuracy, higher dose rates with flattening filter-free beams, improved conformality and beam delivery efficiency with high-definition MLCs, image guidance with 2D, 3D imaging modalities, real-time patient monitoring, such as those used as surface imaging or optical imaging systems. They might even allow beam gating. In other words, when the patient is not in the position, you can gate off the beam, and when the patient is in a position at a certain predetermined threshold, it can treat the patient, and it can also provide flexibility for fractionated radiosurgery techniques. However, integration of all IGRT tools into SRS requires significant physics expertise and effort for clinical implementation and continuous QA and training. You need to also assess the system accuracy from A to Z. In other words, you need an end-to-end test, which I gave an example of that in this slides. And you need to also develop an understanding of failure modes and limitations for safe and effective patient treatments. Thank you.